understand. Things you'd like to hear again. Yes.
Can you go over the sensitivity for like scotopic and photopic?
Sure. Okay, so the question was about peak sensitivity for scotopic and photopic vision. So scotopic vision on rods, right? There's one photopigment, and only one photopigment. And this is its sensitivity. It's maximally sensitive to green. It is insensitive to red. It fades out around yellow-orange, right? That's that weak light. So what that means is that an orange light at the same intensity as a green light is going to produce a very low neural signal. It's going to weakly activate those photopigments. A green light of the same intensity is going to most strongly activate those photoreceptors. And a blue light is at the same intensity is going to be about halfway in between, which is sort of what you guys saw with your lab results, right? Looking at that threshold is essentially, which would be the opposite of this. So we go on rod sensitivity. Okay. Now, cone sensitivity, we have 3 cones. Right? Short, medium, and long wavelength cones, right? So essentially, to look at photopic sensitivity, we have to take the output of all 3 of those and combine them into one graph. Right? So because of the overlap that happens here, we're going to be most sensitive to yellow light. But we're going to have sensitivity, we're going to have some signal from 400 all the way to 650 to red. So essentially that means that we get by combining the blue, the green, and the red all together, that's the threshold. So we talk about sensitivity. So threshold and sensitivity are the inverse functions, are the opposite of each other. Low threshold means high sensitivity, right? Low sensitivity means you're going to have a high threshold, not very sensitive, right? So if we look at photopic vision, sensitive to blues, most sensitive to yellows, also sensitive to reds. Overall, less sensitive than the rods. The rods are much more sensitive. But again, the rods only have one photopigment that's most sensitive to green and insensitive to red. Does that make sense? Okay.
Can we go over the simultaneous contrast with like Colorado and vision?
Yes, absolutely. So,
I just wrote down. I wrote down that less Colorado inhibition is greater than signal. I don't know if that's right. It was slide 49.
what's that?
It was slide 49.
49?
Yeah.
Okay. So, simultaneous contrast simply means that if we have 2 squares that are equally intense, same shade of gray, right? if we contrast that simultaneously with a surround, that surround exerts lateral inhibition influences on that center square. And the brighter the square around it, the more lateral inhibition there is, the darker this appears. The less intense around it, less lateral inhibition, and so this appears brighter. It doesn't just appear brighter, it actually is a bigger signal coming out of our web.
So is it like, because it's lighter, there's like greater light stimulus? And so that's what
Greater light stimulus, greater inhibition,
Okay.
darker contrast. Less stimulation, less inhibition, brighter contrast. And this is the same thing for all of those. For the Mach bands, same thing. Why does it appear a darker line here and a brighter line there? Brighter line there because there's more lateral inhibition coming from this side than there is here, and less lateral inhibition coming from this side, which makes it darker there. Again, the whole point of lateral inhibition is to enhance edges. Where this starts to change, gets darker, it actually dips. And where this gets brighter, where it stops changing, it actually gets brighter. And I know that says perception, but that perception is based on bottom-up sensations. This is what actually comes out of your eye because of the horizontal cells and the bipolar cells. Same thing with the Herman's grid. All of this is showing the same effect. See a darker illusion of a dark dot there because there's 1, 2, 3, 4 brighter areas exhibiting more inhibition in the center than in between where there's only 2 areas exerting inhibition. Can everybody diagram what lateral inhibition looks like in the retina? Yeah? Okay. Do I do it now? No? Yes. What do you have to draw first? Well, we gotta have some cells first, right? So what are you gonna draw first? Receptors. All right, let's work a bunch of receptors in here. What do the receptors hook up to?
Horizontal cells, bipolar cells,
Yeah. And what's the output?
ganglion cells.
Ganglion cells. So down here we're going to have, let's do them as a square. So we're going to have one ganglion cell for every receptor. We're going to pretend for lateral inhibition purposes. Okay, we know that that's not true. Right? This is a signal going to the brain. All right, so for lateral inhibition, in between there we have a bipolar cell for each of those bipolar, one and two together. And what is their sigma?
Excitatory.
Yes. And then what's the other cell that's involved in this? What is horizontal? That provides the lateral inhibition. And where do they send their output? So what is their job? They're inhibiting their own bipolar cell and their neighbor, right? And we're drawing this in the most simplistic way where it's just 3, right? I mean, it gets a lot more complicated. On top of this, we have our receptive fields with the amacrine cells. But we're keeping this simple so we can understand the mechanisms. Right? So everybody understands what we've drawn here and can draw that. Right? Okay. That's the circuitry, right, for lateral inhibition. Yes, ma'am?
So us being able to draw that ourselves is something we should know how to do too?
Yeah. Yeah, I would think if you understand lateral inhibition, you can demonstrate it. For sure. So now we're going to put light up there. Right? So what kind of pattern of light do you want to put up there? Let's make it simple and double, because then we can just double the other screws. Does that make sense? All right. So in this case, what are sort of the rules about lateral inhibition in terms of how light's going to stimulate our bipolar and our horizontal cells and what their outputs? Let's talk about the excitation of bipolar first. What's this bipolar going to have? What's this bipolar going to have? What's this bipolar going to do? Everybody. All right, what about the horizontal? How do we treat those? This horizontal is going to have what? And this one's going to have? Well, this one's being stimulated by 5 intensity light. What's its output going to be? 5, -5? No, it has to be less than that, right? Because it's getting split 3 ways. Okay? So let's say it's, what, -2, -2, -2 is its output. Let's say that. Does that make sense? Okay. So, what is it doing to this cell? is it doing to this side? -2. I'm worried you guys will look lost. What is this pathway doing over here? -2, right? What about this one? Where is it stimulating? Its neighbor, -2. Its same one, -2. And its neighbor over here, because it's lateral inhibition. What is this one doing? Same thing, right? We have a -2, -2, and a -2. What about this one? Same thing, right? So, this one, -2, -2, -2. Now, what about this one? It's twice as big of the stimulation. So what is its output? -4. So it's going to go -4, -4, -4. Right? It's not going to work out well for us, but that's okay. Should have got my -4. Let's go back and read it, because it's going to give us a negative. I mean, the principle's still the same, but instead of -2, let's just make it -5. Because when we get over here, we're going to have 3 -4s, which is -12, which is going to cancel out to 10, and then we're confused.
I'm confused about writing 2 from.
Just make it up numbers. It just has to be a negative number. I don't want it big enough that it exceeds this, so that it becomes negative. So I'm going to use a smaller negative number. I'm going to use -4.
Okay, these are the numbers you wrote like
Yeah.
on the worksheet.
Yeah, I'm just making up numbers to demonstrate this, okay?
I'm just really confused for a
Just
second.
making up numbers to demonstrate, right? Yes.
Okay, so since we're just making up the -4, could you use -4 every time you demonstrate lateral inhibition?
Sure. As long as that -1 belongs to some level of light, and if you change that level of light, then it becomes -2 if you don't,
Okay.
right? Does that make sense?
So if we were doing this ourselves and we were writing out, we would just make up everything?
Yeah.
Okay.
I mean, let's make it simple and stick with like 5 pairs of -1, 15 pairs of -3, 10 pairs of -2. Let's keep it simple like that and keep it in like increments of 5, and then we can just whatever. 25 would be -5 because it's 5 times 5, and then 25 is 5. Right? Does that make sense? All right. So let's go back. This is -1. This is -1, -1. This one is giving 3. 1, 2, 3. This one's giving 3. 1, 2, 3. This one's giving 3. 1, 2, 3. This one now goes to -2. This one, -2. This one, -2. This one, nothing, right? So, lateral inhibition simply says we add up the excitation and the inhibition, and that is the signal that goes to the brain. That is the signal that goes to the brain. So what is this, the input coming into this one add up to? What does the input here add up to? What does the input here add up to? 5 minus 2, 3. What about 5 minus 3? 2. 5 minus 4? 10 minus 5. 10 minus 6. 10 minus forward. -2, back to 0. Okay? So, our signal, if we were to draw what's coming out, right? Darker, lighter, stays at 2, drops to 1, goes up to 5, goes to 4, goes up to 6, -2, back, right? So for a light pattern, the light pattern looked like this, 5s and 10s, right? But the signal going to the brain is every time there's an edge, we have a darker and lighter area of bone, right, to enhance that edge. A bigger signal going to the brain, not just a bigger signal, but on the other side, we even dip down a little bit to really show that change. When it's constant, we stay at a constant level, but when it changes again, on the lower side of the change, we're getting that dip, and on the higher side of the change, we're getting a bump to enhance that edge, that change from 5 to 10, to make that pop. Stays the same, and then at the other side, we get another change and dip to really enhance going from 10 back to 0. So our perception would be that there would be a brighter band here, a darker band there, a brighter band here, an even brighter band here, right, and a darker band there. Because that's what's going to the brain. Does all that make sense? Like, if you can do that, you definitely understand lateral elevation. All right. Other questions? Like I said, I'll post that to the questions.
Can you briefly go over the center surround and receptive field?
Yes. Why do we have center surround receptor fields? That's the first one. Why do we have center surround receptor fields? Right, so we have to converge from 126 million receptors in the retina down to 1 million neurons. So we have to take a bunch of receptors and funnel them All right, 2 groups of 7 receptors, all right? They have to funnel down into one ganglion cell going to the brain. If we take all 7 and run them down into here, and remember, we're going as high as, like, sometimes there's 90 or 100 of these receptors going into one neuron, right? If we have to run all those in here, and there's a point of light here, right? Or there's a point of light here, can we tell the difference of where that point of light is? No, if it stimulates 8 here or 8 here, all we get out of here is 8. We don't know where that is. We've lost some discrimination. But if we now put in an amacrine cell, so these two on the outside stimulate an amacrine cell, and that amacrine cell is inhibitory. Now, if we have a point of light here, and it's 8, what signal are we getting out of here? Okay, if these are stimulating the amacrine cell at 8, and the amacrine cell is inhibitory, what signal is it going to give the ganglion cell? -8. It's inhibitory. We're stimulating it. It's going to provide -8 stimulation. Does that make sense? An important concept of this, right, is we have to have a baseline environment. All of these cells have a baseline environment. All of these cells have a baseline fire rate, but nothing is stimulating them. They're popping off action potentials. Because if we weren't doing that and we were at 0, could we go below 0? No. So as long as we're sending a baseline firing rate, if we want to have -8, we can shut it down. Right? So say the baseline firing rate of this neuron is 20, right? And we have 8 here, -8 here, what's the output going to be? 12, right? Okay. Now, what if we have 8 here? What is the fire rate going to be? 28. Excitatory 8 adds to the baseline 28. So now, Now, for this ganglion cell, we have created a center with these 3 receptors, excitatory, and a surround with those 2 on either side, inhibitory. It doesn't always have to be, it always has to be center surround, but it doesn't always have to be center on, surround off. Right? So this is center on, surround off. They're always donuts at what levels of the brain, of the nervous system? the retina and the LGN. The retina and the LGN get donut center surround receptor fields. Here, right, now we've generated the opposite, right? Now we have a center off surround on receptor field by changing where the amacrine cell is. But it's the job of the amacrine cells to do that. Yes?
So the amacrine cell is always inhibitory.
Yep.
It's just.
Yeah. So 3 processing cells in the retina, what are they? Bipolar, which is the only excitatory. Horizontal, which is inhibitory, doing lateral inhibition. Amacrine cells that are inhibitory, doing center surround receptor fields. And that lay on top of each other, right? This is how complicated it gets. We're keeping them separate, and I've been thinking about them being on top of each other so that we can understand these processes, right? But in reality, think about me, it's a really complex signal coming into your brain. And we're not even talking about having 3 different photopigments, blue, green, and red, coming in. We're just looking at this like it's one light signal from rods. So hopefully you can begin to appreciate the complexity that's happening in the retina before a signal ever even gets to your central nervous system. We have modified your vision substantially, right? Converged it way down, 126:1 ratio, and modified so you're not even seeing what's actually on your retina. You're seeing an enhancement of it. And yet, our visual world appears very real to us, right? We don't feel like we're not perceiving what's physically there. All right, so we said that there are donut center surround receptor fields at the retina and the LGN. What happens at V1? What kind of receptor field do we see at V1? We start to see lines, not donuts, but we see center surround receptor fields that are angles of lines. How do we get that? How do we go from donuts to lines? Thank you, Emma. We get divergence. We have way more neurons. We now are taking 1 million incoming neurons, and we have 250 million cells in V1. So we can now diverge even more than we converged, right? Go from 1 to 250. And so we can send those signals to lots of places. And send those signals to lots of places. So this green cell that's going to be activated, is the center cell. So no matter what angle line we put across, as long as it goes through the center of it, green is going to be part of that. So green is going to send a signal to every cell in this hypercolumn, because this hypercolumn represents any angle of line that's centered on that part of the retina. And some cells, like the red cells, are only going to contribute to things that are near vertical. Other cells, like this cell out here, is only going to contribute to the horizontal. Right? But taking these donut center surround receptive fields allows us to create a hypercolumn of any possible angle of lines centered on one place. And if we now want to say, hey, this is where the line is centered, it's a different hypercolumn. Right? So if now we're going to say, I want to take a line here and rotate it around this neuron, that's a different hypercolumn. And some of these cells will contribute to this one. Like when we get a horizontal line here, green is going to be sitting something here. That's the divergence, right? So one receptor field can contribute to lots of hypercolumns in order to create these lines. And then it's the pattern of activity, right? It's the pattern of activity in these columns that our brain is looking at and binding. That was the last thing we talked about, the binding problem. That when these columns are simultaneously active, they have synchronous activity, our brain ties all that activity into one sort of object and builds it through V2, V3, inferior temporal cortex, down into the temporal cortex to understand what is that object. And if it's moving or we need to respond to that object, then we're taking that same building process and going dorsal into the parietal cortex. Yes?
So these hypercolumns are at the V1 level. That's what we're looking at right now. Okay, so if we're just looking at the level of like the retina, those receptive fields overlapping to produce the LGN receptive fields, how is that different from?
There's really no change in receptive field from the retina to the LGN.
Okay.
Because there's no divergence, it's just a one-to-one sort of thing. What we see in the LGN is two layers that are magnocellular involved mainly with movement detection, and four layers that are parvocellular that are mainly detail, color, precision oriented, right? So, and the two eyes have come together. So the nasal part of my left eye and the lateral part of my right eye are now together in my LGN, okay, on the right side. So the LGN, like sort of its role is consolidating the two eyes, bringing them together, separating out the magnocellular and parvocellular pathways, and regulating that signal. So we have top-down influences, mainly of arousal state, on whether or not I'm adapting or not adapting to stimuli, or paying attention to visual stimuli or not paying attention to visual stimuli. What signal, it's almost a regulatory filtering. What is the cortex and the brainstem allowing to continue from LGN into V1? So if you're drowsy and you're watching the soccer game, you may miss some passes or not see some action that's happening. And if you're really hypervigilant and really paying attention, then you're letting more of that vision through your thumbs. But the center strand receptive fields don't change till V1 because that's where we get the divergence. Because we have the space to do it.
So like the receptive fields for the LGN would just be like magnocellular and parvocellular.
Center surround donuts.
Okay.
And then after V, so in V1, we have simple cells like this, it's a simple cell, but we also have some more complex cells that respond to low, medium, high spatial frequency, respond to selective movement, angles at selective directional movements, angles of lines at certain lengths, and angles of lines at certain lengths with directional specific movement. All of those are the primary features that are then going to go to middle temporal cortex for better movement perception, or inferior temporal cortex for object formation. And then from inferior temporal cortex, IT, where does the signal go? Yeah, so it's in the ventral pathway, but what are some specific brain areas we talked about where it goes? What do they do? Now that we've formed sort of basic objects. The fusiform face area for facial recognition or emotionally important stimuli, and the parahippocampal place area for object identification. So two separate sort of pathways, one dedicated to very emotionally important stimuli, typically faces, another one to object identification. And then we talked lastly about top-down influences on all this activity. So this activity is not, it's bottom-up driven, since it's signals coming in from the retina and LGN, stimulating those columns in B1 and B2 and B3, but then we can have selective attention. Or we can have inattentional blinks where because we're tasking our brain with a different process, we're not actively perceiving or being aware consciously of the incoming signals. But at some level, those signals are present because if I change the number to a different color, it pulls it out of that blank. Right? So we talked about some top-down influences on our perceptions. The big point there, and the whole thing with like the motion-induced blindness experiment, is even though at our level of perception, we're not seeing something, that signal is still coming in from our eyes. And so if we change that signal, all of a sudden we can yank it out of that subconscious into our conscious awareness. Real important to be able to understand the relationship between psychophysical studies and physiological studies. What does that mean? What are psychophysical studies? Yeah, it's our perception to a stimulus, right? What is our perception? What is a physiological study? Our brain activity in response to a stimulus. And understanding the brain activity, the level of brain activity, what's going on at that brain activity level is what generates the psychophysical, right? So when we did the binocular rivalry, whether or not the monkey was perceiving the butterfly image or the starburst image related to whether or not the IT neuron for butterfly or for starburst had more activity. When the starburst had more activity, the monkey said, I see the starburst. When that activity went down, the butterfly activity went up, the monkey said, I see the butterfly. Right? So understanding that relationship between brain activity and our perception. Same sort of thing with this, right? When we did adaptation, right? Staring at these, and then I switched to these, and they show the opposite direction, and then they right themselves. It's because when we stimulated with this area here, we were suppressing this activity. It was adapting. It was becoming less. We were fatiguing that area of the brain because we're staring at those slanted lines over and over again. And so when I show you a straight line, there's more activity on this side because it wasn't fatigued. So we initially perceive the line as the opposite angle until we recover from that, and it goes back to the normal tuning curve and it becomes straight up again. Again, that's, physiological. What is the tuning curve output? What is that column's output doing? Totally drives our perception of, we perceive a line of the different angle, and then as it recovers, we perceive it as righting itself in straight. That's the psychophysical part. The physiological part is this. We talked about another change in tuning curves with practice. You can get better at discriminating something, right? So we talked about this. At first, monkeys can't tell this shape is different from this shape. And if we look at their neural activity, these shapes don't generate different neural activity here. But with practice, of looking at this over and over again and getting rewarded and not rewarded, we train, right, a neuron to respond to just this and to not respond to similar things. And when we generate that brain activity, we now increase our ability to discriminate between those items. But we can't discriminate between them if we haven't generated that signal. All of that ties into right? All that ties into this. So, adaptation, we alter the tuning, we alter our perception of that stimulus. That's the adaptation thing, right? Training, we go from a broader tuning curve to a more narrow. Perceptually, that increases our ability to discriminate between these different lines, to tell the difference between this and that, right? Because this activity and that activity is much different than this activity and that activity. So by sharpening tuning curves, we increase our discrimination. And by paying more attention, right, we can turn up the volume on certain columns, and then that makes us easier to perceive that than before we were paying attention. Good? So, this is really, I keep saying this, but this is like what the point of this course is for you to better understand how brain activity underlies our behavior, particularly in this course, the behavior is our perception of the world and how we respond to it. Okay, other questions? I feel like I'm talking too much. Will I talk about this? Yes. So, we start to sort the signal from the retina start to take the output from the retina and start sorting it into this signal came from my fovea, my center of vision, with less convergence, more detail, more color. This signal came from more of my periphery and is mainly focused on movement perception, so we start to sort out movement versus precision. And in the next content section after this exam, we'll talk about movement, and I'll show you how using, again, processing neurons in the retina, another role of amacrine cells is that we can generate signals out of the retina that are for movement in a single direction. And that's what's going into the magnocellular level, are those movement signals coming out of the retina. We haven't gotten there yet. We'll get there in the next section. But there is more processing that's going on in the retina to generate movement-specific signals coming in. And then these signals are what's going to go to those hyper-complex and complex cells that respond to directionally specific movement in V1. So, this is sort of P cells or precision, detail, color. They tend to not adapt. They tend to always be firing to produce a consistent signal. M cells tend to be on and off because they're responding to movement. So when the movement moves, we want the cell to quit firing and another cell to fire, right? Is that enough on that, Ken?
Yes.
Okay. Hey.
I was wondering what the format of the exams.
Yeah, so you'll have multiple choice to test your knowledge base, right? You'll have some free response questions, and then you'll have a bigger sort of essay question. And the multiple choice is about half of the score, and the free response essay is about half of the test. Yes?
Are there any like times when it would be appropriate to respond with a drawing, or do you just want
Sure.
writing for everything?
No. I don't care if you use bullet points or draw a table, or draw a diagram. If it answers the question, if it demonstrates you understand the material, that's all I want to know. Exams to me are just, they're an opportunity for you to demonstrate you learn the material. It's not a trick, I'm not trying to trick you. There's one correct answer for each multiple choice. You either know the content or you don't. It's not a trick, right? It's just an opportunity to demonstrate that you learn the material. I feel real strongly about that. If everybody in here learned the material gets an A, we will celebrate. I don't care. I don't care about grade distribution. You earn what you earn. Yes?
So the ganglion cells that have the two signals, do the signals go to the optic nerve?
They are the optic nerve.
And then what? Like,
And the LGO.
Okay, but you said those signals aren't, they don't go to MRP cells, like those are completely different?
No, these ganglion cells are going to be labeled MRP coming out of here.
Okay.
Pretty much everything we've kind of talked about is P because we haven't gotten to movement. But in the next exam section, I'll show you some ganglion cells that only fire when something's moving across the retina. And they don't fire if it's just a point of light that's not moving. So it gets a lot more complicated.
So they're labeled as whatever, MRP cells, and then divergence happens.
Well, not divergence, I would say more consolidation happens at the LGN. So we're consolidating the M's together and the P's together and the parts of the two eyes together, right? Left eye, right eye together, but not really diverging. And then when we get to V1, that's when we get divergence. Other questions? Visual transduction, we're all good on that?
Can we go over that a little bit about like how it goes from the left and right visual fields and then to the contralateral sides of it?
This?
Yes.
So, again, half of each eye is receiving each visual field. My lateral part of each eye is perceiving the other visual field. Right? The other visual field. So if something's way over here, right? If I close this eye, I can still see that with this eye, right? And it's coming into this part of my eye. If I come over here, it's now coming into this part of my eye, right? And so the medial, the lateral part of the eye is receiving the contralateral input, right? So it stays ipsilateral because it's already got the contralateral input. It's already getting the red on the left. The nasal part of the eye has to cross over to meet up with that so that we get a unified signal that is red, right visual world, and left visual cortex. The binocular rivalry, when you took that mirror and put it like this, right? You're making a different red signal here than the red signal here because of the mirror. And so your brain is getting two different signals here. And so it doesn't know how to respond to that. So it flip-flops back and forth between perceiving one or the other. Because you're confusing it, right? You're creating double vision. Is that good? Pathways. Secondary pathways, superior colliculus for vision tracking, subconscious, right, the lower level of consciousness. The pretectum, what does that do? Pupil dilation, so it has to know how intense is the light coming in. Is it intense? Dilate the pupil, constrict the pupil. Is it low levels of light? Dilate the pupil. And then the hypothalamus is for light regulating our sleep-wake and circadian rhythms. It does not go to the LGA, it goes directly to these areas. It's below our level of conscious awareness. You're not consciously aware of how much your pupils are dilated or constricted. Visual transduction, 3 steps. We have dark current that happens when? When is dark current happening in the retina? In the dark, when there's no light. Well, it's called dark current. No light, there's current coming in, there's sodium coming in, depolarizing those cells, causing them to release inhibitory neurotransmitter. Light hits a photopigment and activates it. The photopigment releases a signal to close that sodium channel, stop the dark current. We're now no longer able to release inhibitory neurotransmitter and signals go to the brain. How complicated is this system? We're like turning off inhibition here. There's a lot going on, right? Which is why I think it's important that you compartmentalize these things and not try to think big picture about how does all this intertwine, right? That's for like a PhD in vision. Right? Someone's studying at that level. But understanding these bits and pieces, transduction, removal of inhibition through a 3-step process. Right? Lateral inhibition, enhancing changes in intensity through the horizontal cells. Center surround receptive field, it's happening through animal cells. Helps maintain some acuity, even though we have to diverge. We can at least get 2 signals out of one neuron instead of just 1 signal. Other questions? I restructured this course a couple of years ago, and I think that I've got it into manageable chunks. I know it seems like a lot, but there's only 5 lectures, right? So it should be a manageable. It's a lot. I know it's a lot of stuff, right? But I think it's a manageable one. And we'll try and keep it that way for each other. I think have another exam in about 2 weeks. Any other questions? If you have questions over the weekend, if you want to stop by my office on Monday or Tuesday, that's fine. If you know you want to come by, shoot me an email later when you want to come by so I can make sure I'm there. If I have a meeting, I can schedule it for time. If you want to shoot me an email about questions, I'm here to help you make sure you understand this material. I'll stand up here for 15 more minutes if you guys have questions, but if you're really done, you don't have to do that. And like I said, I'll post both of those pictures right now. There's probably some whiteboard photos from other years up there. If you see something like, I don't remember that from class, it's probably just something I did another year that I thought might be helpful.